Okay. Okay, let's get started. Okay. Now, in the last hour, we already know the how to acquire the coefficient, right? And how to calculate the probability of y equal to 1 by using the coefficient and the x values, right? That's what we learned in the last hour. Just like in the linear regression, we actually can represent the model by a line in the x and y plane, right? Well, when we have a simple linear regression, we have we can actually plot use the actual x and y to plot the data point, and actually we can plot the model by a line, right? This formula b0 plus b1 x1 as actually can be represented by a line in the xy plane, isn't it? Right? Well, there's a similar situation in logistic regression. Okay, and in this case, I think we don't have too much time to explain the code. Just look at when you plot the line, the model is actually a straight line in the x space, right? Now again, here we have only 3 variables here, right? Only x1, x2, and y, okay? And in this plot, as you can see, when we have that b1 and b2 and v0, we actually can draw a line in the x1 and x2 plane, okay? And here, every point is a data point, right? This is the data point that we take from this data frame. So every point has x1, x2, and y, okay? So, and here, x1 is the horizontal coefficient, horizontal coordination, right? And the x2 is the vertical coordination, right? Okay? So, where is y? Okay. I mean, sorry?
Professor, what do we do with statistical outliers here? Because there are like a few points up the chart that are definitely moving this line upwards. Do we get rid of them at some point, or do we take them as valid as all the other points?
Actually, this is the representation of this formula, right? When you have the y equal to this linear combination, and in the x1, x2 plane, you can draw a line like this, okay? But the point that I want to point now is that here you have x1 and x2, right? Because you can you have the x coordination and the x1 coordination, x2 coordination. How can I represent y? Because y only have 2 values, right? It is either 0 or 1 in linear regression, in logistic regression. Okay? So I use color, right, to represent y. The green point is kind of like y equal to 1. The red point is kind of like y equal to 0. Okay? So when the model estimates this coefficient, basically it is actually trying to find a line, find a straight line like that can divide the y equal to 1 and y equal to 0. as accurate as possible. Okay? It means that when just like in the linear regression, when you find this line, you find a line that minimizes the error between the estimate value and the actual value, right? This is for linear regression, right? But here in logistic regression, we are going to predict the value of y, right? But the value of y only have two values. It's either 1 or 0, right? Isn't it, right? So we want to find a line that can distinguish y equal to 0 and y equal to 1, okay? As accurate as possible. Of course, there will be some error, right? As you can see here, right? Okay. So this line is actually log it equal to 0, which means that the odd would equal to 1, which means the probability would equal to 0.5. Okay, so this line is represent the point that the estimated probability of y equal to 1 equal to 0.5. Okay, so all of this point, their predicted probability is higher than 0.5. Okay, so we basically, if the predicted probability is higher than 0.5, we'll say that we predict it as 1 or predict it as positive, right? And when that is lower than 0.5, we actually just predict them as 0 traditionally. Okay, so the reason that we call logistic regression a kind of linear regression is because that it still has this linear relationship between x and y, right? Okay, but this time the line is drawn on the space of x. This is x1, this is x2, right? So in the x space, the method was kind of find a line to distinguish the point of y equal to 1 and the point of y equal to 0. Okay, and the way it do it is try to draw a line of y equal to 1 equal to 0.5. Okay, actually besides this line of 0.5, you can actually draw a line of the probability equal to 0.6, probability equal to 0.7, 0.8, and 0.9. Okay, and it's the same way you can draw a line of this 0.5, right? 0.4, 0.3, 0.2, 0.1, right? Okay, so the reason that we want to build a model is that given x and y, we want to estimate the probability of y equal to 1, right? So in this chart, you can you can see that given any point, given any combination of x1, x2, and x2, you will have an idea about what the probability of y equal to 1 is approximately equal to, right? For example, if I have a point here that lie on this line, then I would say that given this x1 and x2, the probability of y equal to 1 equal to 0.9. Okay, and for every point that lie in this line, I can say that the probability of y equal to 1 equal to 0.8, right? So with that, you can have an idea. So this 4 point, the probability that the y equal to 1 is predicted to be higher than 0.9. Okay? And for this 3 point, their probability of y equal to 1 is larger than 0.8 but lower than 0.9, isn't it? Right? So in this way, given any point in this space, for example, here, okay? So if I have a point here, what is the probability of y equal to 1? Anyone? I mean that this is y, the probability of y equal to 0.7, and this is probability of y equal to 0.8, right? So if I have a point here, in between that, approximately what is the probability? Yeah, 0.7 something, right? 0.75 or 0.7, right? Okay? So this is how model works, right? It fills the brains, right? In your sample, you only have some data point, right? But when you build the model, it's kind of like for any given x1 and x2, you can tell the probability, isn't it? Right? So that's why we want to build a model, because in the sample we only know some combination, okay, of x, right? So with the model, you can actually use the model to estimate all of the combination of x, right? That's why we want to build the model, right? Okay, so I think this, as you can see, that the code is not very complicated, right? As long as you are familiar with some basic mathematical things about the log function and also the exponential function. Okay, so there are some easy transformation between here. Okay, so I don't have time to go through the code thoroughly, but actually it is a very good practice, right? If you really want to understand the mathematically underlying logistic regression, right? This is very good practice. If you can draw this line, then you have a very good understanding about what is logistic regression, the mathematics under the logistic regression. But here are some examples, right? What do the blue and cyan means line means, right? And as I told you, this blue line indicate the point that probability equal to 0.5, and this is 0.6, 0.7, 0.8, 0.9, okay? And so in this way, when we draw this line, then given any point in this space, we can approximately know the predicted probability of y, right? Isn't it, right? So as I already explained. Okay, any question? Okay. Now, again, here I do some chart to give you a better idea about the relationship between probability and R. And this is the transformation between probability and log. Okay. As you can see that the range of probability is always between 0 and 1, right? 0 and 1. But the range of R is from 0 to infinity, okay? The range of log is actually from infinity to negative infinity, okay? So that is this mathematical formulation, and I try to visualize all of this mathematical equation in chart, right? So because we have R, and it's kind of easy to do this, okay? And the last thing I want to do here is I don't have time to go through the codes, but I want to point out that for logistic, this is actually the chart of logistic function. So the horizontal axis is actually the logit. Okay, it's actually the linear combination. Okay, which means that it's the f of x. Okay, it's the f of x. So here is the linear combination, and as we can see that a linear combination, the range of that linear combination can actually expand to minus infinity and positive infinity, right? Okay. But what we really want is to predict the probability of y equal to 1. And probability has to stay in the range between 0 and 1, right? Probability has to be within 0 and 1, right? So the logistic function actually transfer the logit, right? It transfers the logit into probability, okay? So it basically just flip this function. It's the anti-function of this one, right? So here is the logit, and here is the probability. And so here are the linear combination, and here is the probability. Okay? So given x1 and x2, and given the coefficient, you actually can calculate the logit of y equal to 1, which is here. Okay? And then with this logistic function, you can convert the logit back to the probability, which is what we really want. Okay? And as you can see that, when the logit is larger than 5, this line would like approach to 1, right? It cannot exceed 1, right? So when the value is lower than minus 5, then the probability is actually approaching 0. Okay? So although the linear combination, the range of linear combination is very wide, right? The sensibility, the change of probability mostly occur in the interval between about minus 5 to 5, right? Okay? So when it is below minus 5, the probability is basically very close to 0. When it exceeds positive 5, then it's approximately equal to 1. Okay? And how about the logit equal to 0? I mean, if the logit equal to 0, what is the probability? Anyone? Okay. Sorry? Yeah, 0.5. Okay? Okay? So when logit equal to 0, okay, it means that the R equal to 1, isn't it? Right? And when R equal to 1, it means that P and 1 minus P are equal, are the same, right? Okay? So it means that the probability equal to 0.5. Okay? So this is the logistic function, and it basically transfer. Sorry, I should. It basically transfers this linear combination back to the probability of y equal to 1. Okay, and when this linear combination is equal to 0, the probability equal to 0.5. Okay, and when this linear combination is more than 5, greater than 5, then the probability is close to 1. Okay, and when it is lower than -5, the probability will be close to 0. Got it? Okay? So this is logistic regression. Because we are now predicting the probability of y equal to 1 instead of predicting y itself. Okay, we need to do a transformation from this linear combination, okay, back to the probability of y equal to 1. And it basically uses this mathematical form to do the transformation. Okay, and this mathematical form is logistic function. Okay, as we draw at the end of notebook of this notebook. Okay, so the definition of logit and logistic function is actually here, right? And what is the relation between them? It means that with this logistic function, we can transfer logit back to probability, right? That is their relationship. Okay. We use logistic function to convert logit back to probability. Okay. So the last question is when this thing equal to 0, we already know that the probability will equal to 0.5. Okay. All right. So this is notebook 1. Any question up to this point? In this notebook we want to like explain the elaborate on what is logistic regression and its basic mathematical things, right? It's a little bit complicated than linear regression, but actually the transformation is quite straightforward. But you just need to take some time to get familiar with it. Okay. Now let's go to the notebook number 2, which is 10B. Okay, it's notebook 10B. Now let's execute the first block, and then the second block, and the third block. Now, again, we have a data point, a data frame of like 131 observation, and here is actually this is actually the case of predictive medication, okay? Preventive medication. This data set is actually coming from an insurance company, right? Health insurance company, right? As a health insurance company, because in the United States, it's not like in Taiwan, right? You actually need to buy the health insurance by yourself. Okay, so every time you go to hospital, you actually can like fill in some application to apply for the medical care expense, right? Okay, so the insurance company actually for every member, it has its kind of like hospital records, right? Okay, so for example, how many days it like stay in the hospital, it's inpatient days, right? ER visit, okay? How many times you go to emergency, okay? And how many times you visit the office, and all of these are the for every members, okay? Every data point represent insurance people, insurance buyer, right? Owner, right? Policy owner, and the ID is actually the member ID, right? And here is actually the hospital record, right? And the last variable, poor care, it means that actually these are not old policy owner. They are the policy owner that have diabetes. Okay, let me see if I have a slide of that. Okay, so they are actually the diabetes patients. Okay, this data is actually a kind of like diabetes policy owner. Okay, and the poor care means that it is not the medical care in this patient is no good. Okay, you know that, but diabetes is a kind of disease that have a lot of complications, right? If you do not, if you care for it, if the medical care is good, right, it actually will not have too much problem, right? But if you do not, if you have a poor care, you can go blind, right? You might need to do, you might lose your hand, lose your legs, right? So diabetes, if you do not have a good care, if you have poor care, then your medical expense will be very, very high, isn't it, right? Your risk of complication will become very high. So as an insurance company, you want to know for each of this diabetes policy owner whether they have a good medical care, right? And how to predict that? We have their medical records, right? So we try to build a model, okay, that we can predict the diabetic policy owner whether their medical care is good or not, right? That's the reason that we want to build this model, okay? We want to use the diabetes policy owners' medical records to predict whether they are good care or bad care. The probability of their good care or the probability of their poor care, actually, okay, because this variable is 1 equal to poor care, okay? So if the probability is high, maybe you want to take some action, right, to do some preventive care so that they won't, their expense can be reduced, their risk of complication can be reduced, and so is the expense, yeah?
That's right, I've never worked with insurance. What is it made for? Is it to predict the pricing of the insurance programs, or what would be the use of it in like real life?
Well, actually, we will do that in next week, okay? And this week we just want to build a model to predict the probability of poor care for each of these patients, okay? We need to do this prediction first, and then we can think of how to deal with it, right? Later, right? Isn't it? Right? So the basic idea is kind of like the basic idea is kind of like we build a model first, right? So with this model, we predict the probability of poor care, and then when we can predict the poor care, we actually can find a way to deal with it, right? Let me see if I have some slide here. So, I think the basic idea is like this, right? Okay, so we have some existing data, right? We only have one, about 131 data, right? So we use this data to like kind of build a model, right? And in the United States, a lot of people have diabetes, right? So you may have like 1 million policy owner that has diabetes, right? So when we build a model, we only use we actually hire some expert, right? So this expert can read their medical records and label each of this patient as poor care or good care, right? You hire some diabetes expert that then examine the medical record of each of these 131 patients, and they will do the label, right, for poor care and good care. And then you have X and you have Y, so we can build a model, right? So with that model, you actually can like put in the 1 million diabetes patient, right? So for each of this 1 million policy owner, diabetes policy owner, you know their probability of poor care, right? That's the way we acquire the data, we build the model, and use the data to make prediction to all of our diabetes patients, right? That's how a model works, right? In the beginning, you only have medical data. You do not know whether the patient is poor care or good care, right? So you hire some expert to label them, to label these people as good care or bad care. And then with this label data, we can build a model, right? And use this model, we actually given the medical record of all of the diabetic policy owner, we can estimate their probability of being poor care, right? And knowing that probability is important, right? So, and we can take some action on that. And how to transfer this prediction to decision, we will do it next week, okay? So this week we'll concentrate on the prediction itself, okay? Next week, we will teach you how to transfer this, how to how to do this, right? How to define the threshold and do some assumption and simulation, and like we can do the process from prediction to decision. Okay, this is what we're going to do next week, right? So this week we like concentrate on the prediction and the accuracy of prediction itself. Okay. Next week we'll go to this application. Okay. And then so next week is very, very important, right? Okay. Since I would say that it's the most important week of the entire semester, right? Okay. Okay. So this is the idea of this data set, right? Before we do model, right? Now, again, as I told you that we want to know the base probability, right? When we have a data, and now we want to know the probability. We care about the probability of poor care, right? So we can do a table, and we can do a proportional table. So as you can see, that the base probability of poor care is about 0.25. Okay, so this is no model, right? So we just look into y and do an average on y, then we can see that the if I do not make a model, I can still have an idea about the probability of poor care. Right? It's about 1/4 of the people are in poor care. Right? That's the idea of base probability. Okay. Now we have this x, right? So we can build a model so we can do a prediction better, right? That's what we are going to do next. Okay. Let's take a look at the notebook in the browser. Okay, so this is the member ID, and this is the medical record, and here are the our target variable, which is poor care, and you only have two values, right? 0 and 1. The mean is like 0.25, as we can see here. Okay. Now, as I told you, right, when in modern data science, before we train the model, we can split we want to reserve some data to test the accuracy of the model, right? I told you that when we have the data, before we do the model, we split the data into training and testing, right? And the training will be used to like train the model, and the testing will be used to like estimate the accuracy of the model, right? That's the idea, right? So when you actually have the value of y, you can actually call this sample split function call and specify the splitting ratio, right? We specify the splitting ratio of 0.7 so that it would return a vector of true and false. Okay, so there will be 70% of true and 30% of false, right? And then we can actually like subset the D data frame into TR, which is the training data set that we are going to train our model, and the TS is the testing data set, which we were used to measure the accuracy of the model. Okay, so as you can see here, that now I only use for simplicity, right? I for better better understanding, first I choose two variable. Okay, so I use these two variables. There are a lot of variables. All of these variables can be used to do the prediction, but I only use these two. Okay, and I'm using TR instead of using D, right? Say after I do this, I will have three data, right? This is the full data, and this is the training data, this is the testing data, right? Okay, and when I do the modeling, I only use the training data, right? And as I say that for logistic regression, you need to specify family, okay? And again, we can build a model and actually take a look at their coefficient, right? Okay, so now before we go to the model accuracy, there's a thing that I would like to explain, right? So actually, here, okay. In the linear regression, we say that the coefficient basically is the marginal effect of x to y, right? Okay, this is for linear regression when the target variable y is a numeric. But here in logistic regression, our target variable y is a binary, right? It's a binary. So the coefficient actually still, we can still infer the relationship of x, the marginal effect of x to the probability of y equal to 1, okay? But it's no longer the increment of y. Here is like, here in linear regression, the B1 actually is the increment of y, right? It's the increment of y per increment of x, right? It's the relation like that. But for logistic regression, okay, the coefficient still imply the relationship between x1 and the probability of y equal to 1. But the relationship is like here, as I specify here. The exponent of the coefficient, okay, can estimate the marginal effect in odd ratio, which means that, for example, I have this B2, B1, this is B1, right, and this is B2. Sorry, this is B0 and this is B1 and this is B2, okay? Okay, so here this B2 is actually this, the vector, because the vector start from 1, right? So B2 is actually this coefficient. So we take the exponent, take the exponential function of this coefficient. It's actually the odd ratio of marginal effect. Okay? So when office visit is increased by 1, okay, the odd of y equal to 1 will be multiplied by 1.0848. Okay? So it's no longer increment, it's no longer addition, it's multiplication. Okay? And it's no longer the value of y, it's actually talking about the art of y equal to 1. Okay? There are two different, right? It's no longer incremental, it's multiplication. Okay? And the second thing is that it did not multiply to y itself. It multiplied to the art of y equal to 1. Okay? So the thing is like the exponent of for every predicting variable, right? The exponent of its coefficient can estimate its marginal effect in arc ratio. Okay? Because right now we are not talking about the value of y, right? We are talking about the probability of y equal to 1. Okay? So there are basically three major differences, right? The first thing is you cannot use the coefficient itself. The coefficient need to make an exponential transformation first. Okay? And the exponent of the coefficient actually estimate the marginal effect in arc ratio. So when we take the exponent of this coefficient, you need to multiply this to the arc of y equal to 1. Okay? Which means that when office visit is increased by 1, the arc of y equal to 1 would be multiplied by 1.848. Okay, so if the office is increased by 2, then we actually has to do a square, right? Because it's multiplied, right? It's no longer addition, right? So it's kind of like the effects multiply to one another, right? So when alpha is increased by 1, the arc of y is multiplied by this thing, right? By exponential coefficient, okay? And when it increased by 2, then you need to because it's multiplication, right? So you need to square the 1.848, which is equal to this thing, right? And if this variable, right, its coefficient is here. Sorry, let me turn it off. Actually, it's already 11 o'clock. Let's take a break, and then we will be back at 11:10. Okay. Hey, wait. 好，你跟那个楼下讲一下哈。好。
在讲梦话。风水? What? Really? I thought you were talking your sleep. 风水啊，风水。Like how Chinese people organize people. 是做harmonize the environment. So like, wait a second, you were talking about feng shui.
Yes, I just remember.
What? You did something interesting.
Yeah, because I just trying to add my feng shui.
I asked about
Your feng shui.
what do you mean by your? Wait a second, then what were you mumbling about when when you violated Hazel's computer, laptop? Lynn just sexually harassed because Hazel's housework, so. Do it again.
It's like black and white.
So what were we talking about? I'm still curious. What? Balzi. Okay, balzi.
To explore, like, to explore about ourselves. To see that what happened.
可以重新翻译一下。他刚才讲八字，包子，命盘，包子蛋，是讲是命盘吗？我感觉像大部分哦八字，哦八字，哦八字，哦。I thought you were talking about 字，like 8 characters. 您。为什么连我都听不懂？You understand, right? No? Are you Vietnamese?
Yeah.
Okay. You can't say. It's like shut up.
您。
我还讲越南。
Yeah, 您。
您。您。What's the difference? 您。That's the only.
我也要。
Other than so what we're talking about when you caress your laptop, your
No, I'm not curious.
So you're talking about your meal plan, bats. And what about it?
Because I don't know where students is going to give it to, so I just have to. So I just had to talk to you.
Such a
I don't know why about.
bats.
Bats.
Okay. And what did ChatGPT say?
No, it's secret.
It's secret. Aww. That's just disappointing, Len. I think you're going to be a doctor. A doctor?
Well, if I have another life.
Because this is your signature? This is definitely a doctor's signature.
Easy.
Like everyone's like readable, and hers is like doctor. You should be here,
It
Len.
has.
I know, doctors. Or a pharmacist. Or anything medical.
Actually, when I were in high school, I also wanted to become a doctor because I really like the movie. But then I realized that I I don't like Korean. So, yeah.
I thought you were like, you're not Korean.